Hello once again, everybody. I'm back again with another kind of special topic. Namely, this was something that I think is an interesting problem that has a lot of people, scratching their brains about, and it's covered quite extensively in Goldstein, his book on classical mechanics. This is specifically from the third edition in sections 3.1 and 3.12. Those are the ones I'm going to be referencing. 3.1 being just the general two-body case, just to introduce some foundational concepts pertaining to how these types of body problems work, and then we're going to bump it up a notch by looking at the three-body problem analog. So, first and foremost, whenever we're discussing two bodies interacting with one another in some sort of space, we typically want to describe their positions relative to one another with position vectors, right? So we have two primary position vectors with these two bodies, here and here, mass 1 and mass 2. Now mass 1 has a vector r sub 1 and mass 2 is assigned a vector r sub 2, so we can describe their positions. The center of our difference vector r is designated with this big R vector, which stretches once again from the center of r to the center of mass, or rather I should say from the center of mass of our system to the center of our little r vector, right? Now this particular system has 6 degrees of freedom, which essentially means that it will also have, how many, trying to think of how many equations of motion, not equations of motion, what am I saying? Just double checking Goldstein here. Do it will have 6 independent generalized coordinates. I wanted to remember if it was generalized coordinates or something else. So there's going to be 6 generalized coordinates for this particular equation. In other words, you can write this particular, the equations of motion for this system using any one of those 6 coordinates, right? So we could have velocity with respect to x, y, z, or x, y, and z prime kind of thing. So if we want to describe the actual motion itself, we're going to look at the Lagrangian of our system, which is designated here with the value L, and we can see that L is equal to the difference between the potential energy of our system T and the the potential energy U, and then our kinetic energy T. I think I actually said that backwards and I didn't mean to. Regardless, once again, it's like midnight, so I'm trying to word good. Essentially, we just define our kinetic energy as a function of the velocities of the mass of the vector between the two masses, our difference vector r, and then also the velocities of the big R vector, which stretches to the center of the difference vector, right, from the midway point of the difference vector. And then we also define the potential energy as a function of the position and velocity of the small r difference vector. More specifically, what we can do is that we can actually express our kinetic energy as being a sum between the combined masses of the system M1 and M2 multiplied by the velocity of the big R vector plus T prime, and T prime itself is the sum of the individual velocities of mass 1 and mass 2. We can also conveniently reparameterize this kinetic energy term, the T prime, when we can rewrite our position vectors R1 and R2. Goldstein skips a fair bit of algebra because he does want to get to the heart of the issue Namely being that you can express our t prime once we know our 1 prime and our 2 prime in terms of just the velocity r squared here, or r dot squared, and in a constant known as the reduced mass. The reduced mass, this term frequently gets rewritten as mu because it's a lot less tedious to write m1. It's a lot less tedious to write mu than m1 times m2 divided by the sum of m1 and m2. You know. But anyway, with that in mind, what we're going to see is that we can rewrite our Lagrangian now in terms of our big R velocity and our little r velocity. And then when we do this, we get our reduced mass term, we subtract off our potential energy like we do in any Lagrangian. And then a fun thing about this is that once we actually employ the Euler-Lagrange equations, which state the following, that I actually get blue here so we can see it in something else. So if our I believe it is our time derivative, the partial derivative of the Lagrangian with respect to some coordinate q, or rather the velocity of some position coordinate q, and this can be anything minus the, I believe it's just the time derivative of, I'm sorry, that's not correct, just the partial derivative. Partial derivative of the Lagrangian with respect to the position of some generalized coordinate is equal to 0. Once we apply that to this system, what we'll see is that our equations of motion cannot be written in terms of this guy here, so we frequently just disregard it altogether, and then we can just simply write our equations of motion in terms of the difference vector and the velocity of the difference vector, the rate of change of position of that particular position vector. So what we get is that the Lagrangian essentially reduces to 1/2 times the reduced mass of the velocity vector, or the velocity of the difference vector squared minus the potential energy. Now, if that wasn't already complicated enough and kind of long-winded to say that we can just express this simply as the kinetic energy minus the potential energy, and then we apply Lagrange's equations, knowing what the coordinates are to recover our equations of motion per Newton's second law, we're going to bump this up a little bit and move into the 3-position case, or the 3-particle case. So instead of working with specifically just 2 masses, 1 mass 2, we're going to throw in a third one in there. We're going to see what chaos ensues as a result of that. So first and foremost, we can really just draw a system of vectors in between each of the masses that we have thrown into this little chaotic system. So mass 1, mass 2, mass 3, right? Mass 1, mass 2, mass 3 each have a vector that corresponds to its position relative to the center of mass, and then it also has another vector that associates it with another nearby vector. So for instance, mass 1 has vectors s1, or x1, which corresponds to its relative position to the center of mass, and it also has vectors s3 and s1, which dictate its positions relative to m3 and m2. This is important because we need to rewrite our equations of motion in terms of our generalized coordinates, in terms also of Newton's second law, because it's easy to express things like that with the general law. So if we remember Newton's second law, if we look at it from a physics 1 perspective here, we get that the summation of our forces, Fi vector, is just equal to 0 normally, or more specifically, mass times acceleration, F equals ma. Everybody knows that one, but I'm not using a for acceleration. Instead, we're using the double dot notation, and that's a good thing to actually cover, and I should have at this point if you're not totally familiar with that. But acceleration, whenever we have some vector designating distance between 2 points. The acceleration of that vector is described by the second time derivative. So we take 2 time derivatives of that vector's position, and so we get m r vector double dot. So if there's a dot above something, it means it's just 1 time derivative, because once again, the derivative of position is velocity, so that'd be 1 dot, and then derivative of, or the time derivative of velocity is then the acceleration. So the second time derivative of position would then be acceleration, hence the double dot, if you're not familiar with that. So, with that out of the way, we describe the acceleration of any of our first particles, so we could say m1 here, for example, can be written as negative g, g being the gravitational potential constant, times the sum of the mass of our first object multiplied by the the difference of our mass of interest's position minus the other mass's position divided by the cube of the magnitude of that particular distance. So we have a vector here, we need to recover a vector here, and that's what that does. So in this case, if we wanted to write this in terms of just the acceleration of our first mass, we would have negative g times the first mass times the quantity of the difference between, let's say, m1 and m2. So this vector here, s1, I believe, or rather we could just actually just write out the coordinates and get what those are. I'm too tired to do this analytically. So we'd have the difference between these two guys here, and then we'd divide that by the cube of the magnitude, or actually how long it is, instead of just the positional difference between the two. Plus, once again, this mass 1 times the difference between the positions of mass 1 and mass 3 divided by the raw distance between mass 1 and mass 3 cubed, right? So then Goldstein's like, okay, we can also rewrite that for any one of these vectors S that describe the distance essentially between m1 and m3, or m1 and m2, or any one of those 3 vectors. It can be written as the difference between the second one and the third one relative to those two. So for instance, S1 here can be described as the difference between S2 and S3. If you do the math, then it should resolve out that way. Moreover, the sum of all of these position vectors ought to equal to 0, because if you add all 3 of these position vectors up and you just kind of trace it in either clockwise or counterclockwise fashion, you're going to end up, once again, at the same spot, right? Because these are, once again, our relative position vectors. Thanks, past me, for writing that out, because I forgot what those were specifically named. Once again, Goldstein does this little trick, and he does a little bit of algebra and skips most of the algebra, and he is able to re-express the sum of the accelerations of these relative position vectors as being some mass times the gravitational potential multiplied by the quotient of your relative position vector of interest divided by its magnitude to the power of 3 plus the mass of our object of interest times our vector big G. I didn't write it out, but this mass term here is the sum of all of the masses, m1, m2, m3 here in this case, or for 4-body, m1, m2, m3, and m4. And then big G vector here is just the sum of all of your individual relative displacement. It is Thursday afternoon, man. Why are you doing that on your motorbike? Anyway, I'm not gonna rain on anybody's parade. Vector. Anyway. Big G vector is essentially just the sum of all of our relative displacement vectors divided by their magnitudes cubed. Now, I'm going to erase this, do a quick little cut, and then I'm going to continue elaborating on what the tar this is going to wind up looking like and what the real conundrum is with the three-body problem. So basically, given the chaos that would ensue in trying to parameterize all of these particular equations of motion together, there were several attempts to try and make some sort of generalized solutions. And one way that we begin to look for general solutions is by looking for specific solutions. One specific solution that was, of course, found by none other than Euler was to place essentially all of our position and all of our relative position vectors, relative displacement vectors along some sort of collinear line, and then have all of our objects move in these elliptical orbits with the same period, tau, right? Moreover, the g vector is also collinear in this particular position. Goldstein does not give that specific formula as a solution in the book, and I recommend looking that up on your own time. I didn't, but there's probably a paper out there written by somebody, or even just whatever Euler himself wrote down, archived away somewhere on how he found and derived this particular solution. The reason why this is a solution that is of interest of us is because it allows the equations to be coupled with one another. That is one thing that is important here whenever we're talking about the solutions to the three-body problem. We want our equations to be coupled to one another because we need to be able to describe the rates of change of position of these bodies relative to one another. The moment that these equations become decoupled solutions to one another, then the motion of one doesn't necessarily depend on the motion of the other. At least that is how I am understanding these things, right? And that's what I wrote down there with an underlined coupled, right? So I don't remember who defined it this way. I don't think it was even Goldstein, but I just looked it up on Google basically. But a coupled equation in layman's terms are some set of equations that are interlinked via their dependent variables, namely how their variables describe a rate of change, and then more specifically the usage of these variables for one equations will always depend upon some other one of those. Besides the point, in the case that Euler's solution typically fails is when our big G vector ends up being 0. When that happens, they decouple and they are reduced to a summation of just the relative displacement vectors, right? This particular failure transpires whenever the masses in our configuration take on the shape of some sort of equilateral triangle. And this can happen at really multiple points inside of the configuration of the orbits about the center of mass here, represented by that dot. I try to draw another triangle inside just to kind of show where it can happen in multiple places. Goldstein's example, which he sourced from another book, I believe it was written in 1999. I can't remember by whom. I'll, once again, if I remember, to link it in the description or write a comment. I will include that, but besides the point, at these points along these orbits, the equations become decoupled, and then they don't tell us anything about the other one. There do exist some asymptotic solutions to these equations, and namely they happen at specific amounts of total energy of our system. If the total energy of our system is greater than 0, then what ends up happening is that one of our masses that's entangled in this wreck gets ejected, and then the other two bodies continue to orbit some sort of relative center of mass in an elliptical orbit. In the case where the total energy is less than 0, then the remaining two bodies that are left behind just continue to orbit one another, with the third one ejected, but instead in a bound state, which just basically means that they're just kind of stuck in this smaller region of space due to the fact that the potential energy therein becomes a local minima instead of a local maximum. So it's a stable equilibrium at that point, and compared to an unstable equilibrium in the first case. And then in the third case, we just have all three of them orbiting kind of in tandem with one another around a common center of mass. It would be like if you had three of them, like if you had your single triangle configuration, except they all shared the exact same orbit, right? Same apogee, same perigee, all going around the same center of mass, basically covering the same amount of space, trailing one another in perpetuity. So as a result of these particular configurations, what you get are these things called Lagrange points in the orbits. And a Lagrange point is effectively points inside our three-body or even two-body system in which the gravitational attraction between the two objects perfectly nicks one another out. So essentially, if you were there, it would be the closest thing to being in pure zero gravity, at least relative to the two largest bodies. And Goldstein included a depiction of where the Lagrange points would be within the orbits of the Earth and the Moon, or rather just some mass 1 here and some smaller mass m2, and we can say it's the Earth-Moon system and just exaggerate those particular things for the equipotential lines. This is a really crazy looking diagram, I know, but essentially what these do is that we can think of these as the behavior of the potential energy of the system, right? So at this point you have all of your potential energy, or your gravitational potential energy pointing inward here around mass 1, same thing around mass 2, and then we can continually draw larger and larger circles around our mass of interest, or the more massive bodies, so it would encapsulate the center of mass. I think this might actually just be around the center of mass. So that's the point. What we get are these larger and larger concentric circles, and at certain points, and these are calculable, we get these Lagrange points that form within our graphs, and we get these really crazy looking equipotential lines. Normally you might see some equipotential lines whenever you're like thinking about the flow of like your electric fields from positive to negatively charged particles, just to create some sort of analog, where you'll have like all of your positive equipotential lines going into your negative, basically electricity sink, for lack of better words. That's just some sort of analog, and obviously the more of them you draw, then it just indicates that there's more potential energy essentially, or they're denser, for lack of better words. The denser the equipotential lines, the more potential is there, typically speaking. That's the way I took it back in undergrad. If I'm wrong, someone please correct me. I'm fine being wrong. I just want to know if I'm wrong. Thank you. Anyway, Goldstein kind of concludes then that what you can effectively generate is a two-body problem where you have a third mass who's negligibly small, and then when you do that, you can describe the equations of motion in terms of coordinates rho, theta, and z, which are just our coordinates in cylindrical coordinates. Because if you want to look at it this way, you're basically looking at the top of a cylinder. So you'll have some radial distance rho. This way I designated it as r, just out of habit. But you'll have some radial distance rho, and then you'll have some sort of rotation of that vector itself around some angle theta, and then your per the right-hand rule, we would have our r theta z pointing out of the board for the right-hand rule to make our orthogonal basis set of vectors. And the solutions to this particular configuration would come whenever our velocities in either rho, z, or theta are all equal to 0. And those are kind of crazy to try and find, and they all really just depend on your initial conditions of the problem. So in comparison to the first problems that we looked at with the two-body problem, is that we were able to generalize a set of coupled differential equations that can tell us information about how those bodies move in any sense, right? In the case of three bodies and more, that's not possible. Instead, we get these really crazy chaotic systems that are hinging on not only just the initial configuration of the system itself, but also we have to bend the rules in order to get some sort of generalized function, like saying that certain points of our configuration have decoupling transpire, or we have to account for areas in which our equipotentials are effectively zero, and you have all of these extra variables that prevent us from getting a single generalized solution, and more importantly, from getting a set of totally coupled differential equations. So it's because of that mathematical mathematical quality of the coupled differential equations, or rather the uncoupled differential equations, which basically happen every single time without you bending the rules, that having a generalized three-body formula just has not happened yet, and we have to solve it on a case-by-case basis. And that is essentially really it for the three-body problem. I do hope this was interesting and that you enjoyed. I know my other videos at the moment aren't really doing too great relative to my other stuff, but I understand this is a wild change in pace from the rest of my content from what y'all are used to. But I do enjoy doing these kinds of videos regardless. It's good practice for me. It's for like oral examinations and just for hammering down general concepts. If there's any other particular topics in physics that you guys want to know about or want to learn about, please let me know about it. I will gladly do it. I will read any topic and I'll present on it, and I just want to make videos about science and anything just to share information. That's just what I'm passionate about. So if there's anything that was unclear, let me know. I tried to describe this to the best of my ability. To be horribly candid, I almost just didn't want to pick up Goldstein. I'm not really a huge fan of the textbook itself. I did not find much in that text to be elucidating to a helpful degree. So if I wanted to actually sit down and teach myself classical mechanics again, I'm just going to sit down and read Taylor, because at least Taylor made some iota of sense. Goldstein just kind of felt like he was talking wherever his brain wanted to go, and it didn't make a whole terrible lot of sense. Like, for instance, with this issue with like two-body motion, you would think you might stick to something more specific like planetary motion, but instead he delves into things like scattering. I know that scattering is important, and it is in the category of two-body motion and two-body force problems, but just overall conceptually it feels like you're kind of throwing a wrench in there, because you're comparing planetary orbits on a macroscopic scale to something that's much smaller. Although I can see the benefit of connecting those things like you would in like thermodynamics, in which you need to connect like a macroscopic quality like temperature or volume to its microscopic counterpart, and how that would relate to the equation of state and its ensemble and the number of accessible states. I'm not trying to make a word salad, I'm more hunting for words when I'm talking, so my apologies if some of this is kind of incoherent. Regardless, I actually tried to look for the solutions or the explanations of this in Taylor first, but Taylor only had the two-body solution, and he didn't feel like wasting his breath on the three-body solutions, because, like I said, there aren't any three-body solutions unless you're solving for a specific case with a specific initial condition. thanks for watching. Thanks for letting me vent about how much I don't like one particular textbook. But yeah, just thanks.